Hi everyone. So today we're going to talk about the separation of variables for spherical Schrodinger's equation, and it's three-dimensional. So this is the first part of chapter 4, and also is very important because it allows us to compute the wave functions for such as the hydrogen atoms. Okay, so let's get started. And let's start with time-independent Schrodinger's equation. So because in this book, most of the times what we concern about is the time-independent Schrodinger's equation. So we know that this is the form of three-dimensional time-independent Schrodinger's equation. And in one-dimensional case, you might see this as del x square. Yes, but three-dimensional is Laplacian, and how to define Laplacian? It is taking three double derivative. Okay, but we only concern about spherical case. Okay, but why? So why spherical? Think about this. Making it spherical looks like, well, it looks like it won't make our life easier because spherical Laplacian is a little complicated, right? So why are we so interested about spherical? That's because we can assume, so most of the times, and also in this case, we assume the potential energy is only related to the radius. So it's not related to the angle, right? And if we're using Cartesian coordinates, x, y, z, we will have this kind of potential energy. And we can't say that, well, it's not related to x, y, or z because it doesn't make sense. But here we can say it only related to radius because most of the particles has some kind of symmetric that allow us to ignore the angle. So why is it so important to have a radius potential energy? Well, that's because solving the differential equation is a little complicated. So we don't want to have a potential energy that involves too many variables. So let's write down the spherical Schrodinger's equation. So here I'm just copying the textbook because here I'm just plugging the spherical Laplacian into the Schrodinger's equation. Okay. So when you're watching the videos, you can speed up or just skip this step. Okay, so now we have this form. So first we assume Schrodinger's equation can be separated to two parts. The first is the big R and the second is the big Y. So the first part is radius part and the second part is angle part. So here is an assumption. Then if you say, what about I have this kind of wave equation? Then we can't do the separation of variables because we have the assumption here. That breaks our assumption. Okay, and then let's just plug in wave equation equal to Ry. So just plug in to this equation. What do we have? Okay, so let's see. So I have to write it a little smaller because I don't have a very big iPad. It might cause a little difficulties in reading it. Okay, so here, again, I am just copying. Okay, now we have this form. So what is this form? Well, what can we do about it? So first, we know that the potential energy is only related to radius. So here we actually have potential energy related to radius and Ry. And energy, well, it's just a constant. Well, it's a number. So let's combine those two terms and then put it in to the R parts. So now we have this. Plus V minus E Ry. So here I'm just combining them because they both have the common factor Ry. And this is the R parts. What about the theta parts? So first we have the h bar squared divided by 2m. Sine theta. Okay, and then plus, oh, we have a third term. So again, we have a h bar divided by 2m. Okay, equals to 0. So here is the angle parts. Which would be, well, okay. And today, in this videos, we're going to only concern about the angle parts. So next time we'll solve the R. So let's look at the angle parts. So if I multiply the entire equation by negative h bar square, 2m over h bar square, basically I will cancel out all the constants in the front, right? And on the right side is 0. So if I multiply it by negative 2m divided by r h bar square, nothing would happen. So I can remove any constant as long as they both have that parts. Okay, so multiplied. Okay, and then now I have a cleaner form. And also there is another thing I can do. So R is related to the small r, right? And the y is the angle parts. So basically del ry, del r, I can move the y out because the y has nothing to do with the radius. So I can move it out. So here I have the big R inside, and I can move the y into the front. And here, well, nothing is changed. And on the right side, I can do the same thing. I can move the R to the front. Okay, I move the R to the front. Then dy d theta. Great. And then here, the same. I move the big R to the front. Okay. So now, divided both sides by ry, and we'll figure out something. Divided both sides by ry. Let me check if I am recording. Okay, yes. And then I'll have 1 over r, because you see the y just cancel. Y divided by ry, y is canceled, so 1 over r. And the r square will still be there. Yes. And then here is v minus e's because the ry just canceled. And then 1 over y because, well, r divided by ry, r is canceled, so it's 1 over y. Okay. Then minus again 1 over y. Here is the same. So, yeah. Okay. So now it's the pretty common separation of variable, because we have here everything is related to theta and phi. Here everything is related to r. So what if I move one term to the right side? Okay, so here. So basically I move the everything related to the angle to the right side. Okay, so now the left parts of the equation related to r, right side related to theta and phi. So we can say they both equals to one constant. Okay, but why? So for example, let's think about x equals to y, right? The left side only related to x, right side only related to y, and x and y, they're independent variables. They're not dependent. Okay, so if I analyze x, let's say I take the derivative respect to x, because I want to say, I want to see if the function on the left would change if I change x. Well, if I take the derivative of x, I'll find that the right side is 0. Well, the right side is, yes, is 0. So basically this function is not changing. And if I take the derivative of the right side, well, I'll find the same thing. So they're pretty independent. So the left sides of the equation and the right sides of the equation, they're independent, so they must equal to one constant. So let's make the constant L multiplied by L plus 1. Okay, but you may think about why. That's because using this form can simplify our calculation. So honestly speaking, I don't know how the physicists discovered this, but I believe using this form is the simplest way that they find. Because I think they might spend a lot of time to find this. So now we have two parts. The first part is about the R. And the second part is about the Y, which is the angle parts and the radius parts, basically. Okay, so now let's solve the angle parts, the angular equation. Okay, let's solve this. Well, first we multiply both sides by sine squared theta. Okay, so now the right hand side will become sine squared theta. Let's see if multiplying by y sine squared theta. Okay, that makes sense. Oh yeah, that makes sense because I missed one parenthesis here. Okay, so in the left side, this would cancel because I multiply by y. So the 1 over y just disappeared. And then I have this form. Okay, one interesting thing. Now I have to make my second, well, maybe not second, assumption, which is the angle part of the Schrödinger's equation is made up by the theta parts and the phi parts. Okay, so here we have two parts. So overall, our Schrödinger's equation is actually three parts: r parts and theta parts and phi parts. Okay, and it's also equals to ry because y include both theta and phi. Okay, so let's write it down. So we know that y is equals to theta and phi parts. So here we have this. And this. Okay, great. Okay, and we divide it by the big theta and the big phi on the both sides. So divided. Okay, now let's look at the first term. So because the phi parts are not related to the theta, so I can just move it to the front. Yeah, because you see, okay, I think I made a mistake here. So here it should be theta. Yeah, because there shouldn't be any r inside this equation. Okay, so I move this out. And also here, I can move the big theta out because the big theta is not related to the phi. Okay, so here, after I move it out, I'll have this, yes. And then I divided it by theta and big phi. So yes. So it's really easy to make mistakes here because we have many variables. So I might write something wrong. So hopefully it won't cause many confusion. Okay, sine square theta. Okay, and this will just cancel out, but yeah. And then cancel, and then here we miss one thing, which is we move the big theta out, so the big theta would cancel. Okay. So after it cancel, we have here. Wait a minute. I think something is weird here. So I multiply both sides by sine square theta, but I didn't multiply it here. So the sine square theta would cancel. And here it will become sine theta. Is that right? Yes, that's right. Okay, so here it will become sine square, and here the sine square theta would just cancel out. Okay, because the sine theta here doesn't make sense. And here we have sine theta. Okay, now it finally makes sense. So now this part is only related to theta, and this part is also theta. So this part is phi. So well, we know that they must each equals to a constant, because if I move this part to the right hand side will be only related to theta. The left hand side will be only related to phi. This should be phi, right? Okay. So they must each equal to a constant. So let me name one constant m square. Yes, m square. So I said this part plus this part equals to m square. So now I'm just copying. So I have to write the theta very big so that I won't treat it as small theta. Yes, here we have it. Sine square theta equals to m square. And then the big phi parts would be equal to negative m square. Oh, why is negative? Because if I move this side, if I move this to the left, I'll have this plus this, and it is equal to m square. So if I move the big phi to the right, it will become negative. So here I'll have a negative, and if I move it to the right. So it will equal to negative m square. So let's solve those two equations. Now we have two differential equations. So let's talk about the second differential equation. So because here the solution is easier. So if I multiply both sides by the big phi on the right, I will have negative big phi m squared. Or let me write it in this form. Okay, this looks very familiar. This is actually a differential equation, right? second order differential equation and very classical, who has a general solution of this. But wait a minute, this looks a little different from the textbook, right? The textbook says the solution would be this. Okay, so why? First, we allow the m to go to the negative. So the m can both be positive or negative. Okay, so now we don't have to concern about this case. We allow it to go to positive or negative. Secondly, the constant a in front of the exponential, we can let the big theta absorb it. Okay, what does it mean? It means whatever the a is, I want to put it into the big theta equation. Because remember, the wave function is equal to ry, and ry is equals to r. Okay, let me write it into this form. And it's also equals to r big theta and phi. So if I have a constant a into the big phi, I can move the constant a into the big theta. So I let big theta absorb the constant. So now I have this as my solution. So now we've got the phi equation. And we have to deal with theta. And also, we know that m has to equals to 0 and plus minus 1 plus minus 2. Well, it also depends on the value of L. But why? Why m must be an integer? That's because the periodic nature of this function. So we know that if we add 2 pi to phi, it must equals to the value of the function won't change. Why? Because if you're in the spherical coordinates and you're talking about this angle phi, if you're talking about adding 2 pi, so it's exactly 360 degrees, so one round, you have to return to the same value. Otherwise, it's not a normal spherical coordinates. So by using this properties, we can get m is equals to integer. Okay, if you don't believe it, let's plug it in. Okay, so here for phi, I have phi plus 2 pi, and it's also equals to itself. Okay, and for exponential functions, you know, we have a plus here. I can write it this way. This is the property of exponential. And then if I cancel out, this will be 1. Yes, 2 pi m. Okay. And now, if we solve for the value of m, we'll find that m has to be an integer, right? Because, so if you have taken the course complex variable, then you know the solution for this equation would be integer. And then let's return to the theta function, because now I only know the phi parts. I don't know the theta parts. So the solution of theta would be Lagrange function. Okay. It is equals to a constant, the A absorbed from the phi equation. And what's this? This is associated Lagrange function. And it's defined by, well, this quite long definition. And you might have one question. Why? When we solve differential equation for B, we just solve it. But, well, how to say it? When we solve this kind of differential equation, we know how to solve it because we already solve it in the differential equation course. But how do we know this is the solution for big theta function? Well, I believe there's a proof for this, and there's also a long path which those physicists or math scientists take to find this equation. But that's not covered by this book, and also it's not covered by the introduction of quantum mechanics. So we will skip that for now and memorize the results. So usually in the exams, the forms of Lagrange polynomials is given, which is this. For example, Lagrange polynomial with L equals to 2 is equal to this forms. But here we have cosine theta. So eventually we have to substitute the cosine theta, substitute x by cosine theta. So here, right? And then plug it in. So after all, if we write all the things together, we have this conclusion. Well, it's exactly the same as the forms you saw in the book. Okay, but wait a minute. How do we get this? This looks quite unfamiliar, right? Okay, we didn't show, so I didn't show the steps to this. It's just the form of constant A. So by a lot of computation, so those scientists try different values of L and then discover a form for A. This form guarantees that the wave function y can be normalized. So this is very important because the normalization is a necessary condition for wave function. Otherwise, it won't make any sense. So here is also a conclusion that we have to remember, but I strongly recommend it to discover it a little bit about how scientists find this constant. So it's a pretty mathematical problems. And then now we finish the parts for y, and we still have r, but that's the whole parts of today's videos. So wave equation phi is equals to ry, and now we have y, and r will be in the next video. Thank you.